Hey everybody, it's Dr. Jensen and CCJ 3701, Research Methods in Criminology. So today is kind of more of a straightforward lecture. I'm going to try to move about it in a good pace, but this is one where you kind of just want to sink your teeth in. I encourage you to jot down some notes or questions you have while you're listening. So that way when we go into SPSS, you can start to see the pieces working, and you can clarify anything that's maybe a little unclear. We're going to be learning two regressions in this class. This is the first one. These are multivariate techniques. So let's just jump on in to OLS regression. So first we're going to review what it is. OLS actually stands for ordinary least squares, and we're going to use and interpret some OLS regressions so you can see how they work and how you use them and what they mean. So first, OLS. If you hear people say OLS regression, or they say linear regression, or just plain regression, it's all usually the same thing, okay? So it's assessing, is X related to Y? Does X cause Y? Is Y a function of X? How Y varies with X? Or testing lots of multivariate relationships where you're loading lots of variables in to your Q and SPSS. You want to control or test for lots of other things that you think matter. Okay, so when we say X and Y, we're actually referring to your independent and dependent variables. So X is the independent or your predictor variable, and Y is the outcome, your dependent variable. Okay, so we want to know if knowing this about you, the independent, helps us predict that about you, the dependent. Maybe they don't, maybe they're not related at all. But if they are, we want to know that relationship, and we also want to know how it works. So remember when we learned how to do like frequencies and counts and percents and stuff? Those are the univariate statistics. They just tell us about one variable. When we run bivariate statistics, they test a relationship between two variables and let us know if there is one. They also tell us a little bit about the variables. But then multivariate statistics, like OLS regression, they not only tell us about the variables and if they're related, but they tell us how that relationship works. You know, this increases as this decreases, or this changes when this changes. So we know kind of how to use it. So the only times you can use OLS regression or linear regression is when your dependent variable, your Y, is continuous and normally distributed, meaning it is interval. You must have some kind of numerical quantity, a quantitative dependent variable. So here's some examples. Maybe you want to predict operating budget. Maybe you want to predict how many days somebody spends in a program. Maybe you want to predict how many employees somebody has. Or you want to predict scores on a scale you just built of how many drugs people are using, how many acts of delinquency they do. So you can use it with money, you can use it with time, you can use it with events, anything you want to quantify. Those outcomes that you can quantify in some kind of number are perfect for OLS regression. If you find that your outcome variable, your dependent variable, has more to do with whether something happened or not, then that is a different kind of technique we're going to learn next week. So these are for people that have quantities they want to predict. Okay? So it creates a little formula. It, meaning SPSS and statistics, basically tries to write a line to fit the data to see if, first of all, these two variables are related to each other, and then how that relationship works. So here you see on the bottom, there's a little graph. There is a perfect linear relationship between knowing the temperature in Fahrenheit and being able to know the temperature in Celsius. Okay, we're going to come back to that in a minute. But the formula we use to compute Y as a function of X, or the dependent variable as a function of knowing the independent, is Y is Fx. Or we can literally break it down even more and say Y equals AX, or excuse me, A plus BX. Okay? So if we wanted to know the formula for that line so we knew how it worked, we have to know the slope of the line, how steep it is, and we have to know the y-intercept, where it crosses the y-axis. So this is going to bring back memories and maybe nightmares from your 8th grade algebra class where you started to plot out lines and stuff like that. We use a lot of those same ideas and concepts, but the interpretation is actually pretty easy. So that's essentially what's going on. You're making a line that's going to try to fit the data and fit the relationship of it. So for example, let's say you collected some data from people on their budgets. You said, I want to know your agency's budget. And you plot all of them out on a graph. This agency has a $15,000 budget. This one has a $30,000 budget. This has a $5,000 budget. You know everybody's budgets. That's the dependent variable. And then maybe as a predictor, you want to know how many employees they have. And you kind of figure the more employees they have, the bigger their budget is, but that's not always true. Some agencies are very overwhelmed and short-staffed, and they don't quite have the money they need to function. But maybe you're looking at certain kinds of agencies like court programs or rehabilitation programs, addiction recovery, probation or whatever. And you just kind of want to see how that works. So on the independent variable, you know all of the numbers of employees every agency has. So this agency has 20 employees, this agency has 10, or this program has 5. And you kind of want to see how they relate to each other. So basically, our research question here is, does knowing how many employees you have, the independent variable, help me predict what your operating budget's going to be, the dependent variable? We think the two are related. We're not sure. And then not only do we think they're related, we want to know how they work. So how much more money do you get if you have more employees? And does it work like that? Okay. So a regression line is basically SPSS trying to make a line that helps you make that prediction. So knowing all your answers on X, or how many employees you have, the independent variable, can that help me predict some of your answers on Y, the operating budget or the dependent variable? And the line tries to represent a line that's closest to all the data points, that kind of slashes right through the middle of them. That's the best estimation SPSS can possibly generate to fit the data. Some points are going to be close, some are going to be far away, but that's kind of the very best average distance between all the points. That's all a regression line really is. Okay, that's how it works. So the regression line represents a plot of the slope and then an average change in Y associated with a unit change in X. That's always, always, always how we interpret it. So when I make a change in X, what happens to Y? Okay. When we say a unit change, what's a unit? Well, if X was number of employees, a 1 unit change in X would be 1 more employee, an additional employee. That's it. We want to know how many more dollars you get for every additional employee you have. It visually or quantitatively depicts that relationship between X and Y. Okay. So here's that relationship we talked about before. Here's this beautiful linear relationship between knowing your temperature on Fahrenheit, being able to predict the temperature on Celsius, and vice versa, by the way. So you see how there's a dot right where it says 32? We know that from science, right? We know that when it's 0 degrees Celsius, it is 32 degrees Fahrenheit, because that's the point at which water freezes. Okay, so we know that in order to kind of compute those differences between Celsius and Fahrenheit, there has to be a relationship between the two where we can do that. Okay, so there's lots of really great lines that we can make in science and in real life where things kind of fit together. Knowing this about you lets me predict that about you. Okay, so again, OLS, ordinary least squares, is the line that is closest to all those data points. And I'm going to show you some of what happens when we calculate this line. So this is the very best prediction we can make. If we, didn't know your X and we wanted to predict your Y, we would use something like this to do that. Okay, so Y is a linear function of X. Y equals A plus BX. A is our Y-intercept, where it passes through the Y-axis. B is our slope, how steep it is. And then X and Y, again, are those dependent and independent variables. Okay, so this is how it starts to look. The slope is the average change in Y associated with the unit change in X. So how far up and over do I have to go in order to capture the change in the outcome? Okay, that's what we're doing. And then the intercept, again, is the point at which it crosses the axis. And intercept, or what we call a constant, is kind of the average starting point that most people start from. And you get all these little pieces in SPSS when it gets spit out. So when you see output in OLS regression, you get these little boxes. So once you run a regression, you'll get stuff that looks like this. The first box is model summary, because essentially in SPSS, you're graphing a model of the relationship. So I'm modeling this relationship, what it would look like if I tried to fit a line to it. And these are the parts of that line. Okay, so the model summary has two pieces of information, the R and the R squared. Okay, we use that to tell us how good of a job the line is doing to describe the relationship going on. How much of the dependent variable am I actually accounting for? Okay, we'll talk more about that later, but that's one thing that we report in our result. The second box is the ANOVA box. We always have to do an analysis of the variance in order to calculate all the regression parts. So this box we don't use very much. You don't have to report much from it, but you see it says sum of squares and degrees of freedom and some of the stuff you've recognized in an ANOVA before. Okay, an F value, those are all parts of the equation in order to analyze the variance and know what's going on in there. So we actually square all these little data points that we know about, because if we happen to have any negatives, it accounts for those negatives. Okay, but again, we don't use much from this box, so you can kind of put it aside. The very bottom box is what we use the most. It's called the coefficients box. Okay, in the first column where it says B, that's the B from that little formula. That's the slope. Okay, where it says constant in parentheses, that is the y-intercept. So these are the little parts inside the formula of that line that's representing the relationship between x and y. On the very end, you have sig, where it's meant significance level. Okay, so it tells you whether or not it's actually a significant relationship, and if we can feel good beyond just chance that this is actually true. And we have a very, very low chance of it being false or wrong. So that's the kind of stuff you see in SPSS. Again, don't feel deflated if you happen to not get a statistically significant result. This is how a lot of people feel sometimes. Yes, I'm right. These two things are related. Yay! You know, if it's not related, that's okay. The reason we do research and the reason we measure things, the reason we do surveys and interviews and focus groups, we collect data and then we run little tests in the data, is to test for ideas to see if things work the way we think they do. We make predictions. Those are called hypotheses. We want to see if those hypotheses are right. Sometimes we're right and sometimes we're wrong. Welcome to science. So don't feel like a failure if you find out that it is not significant. If that p-value or that little sig level is way too big, don't feel like you personally failed or you made a mistake. It just means that those two things aren't related. It's still a result. It's still a finding. You found out that something we thought was true actually isn't. Okay? So don't be afraid of finding out something isn't statistically significant. It's still a result. We still write about it and we still interpret it. Okay? So again, if all we had was a bunch of pieces of data from organizations, we had a bunch of dependent variables, like maybe we had a survey that went out to all these organizations, hey, what's your budget? And that's all we had. And then we wanted to go approach another organization and say, how could we predict their budget? But all we have is the budgets of all these other ones. With no other information, the best prediction of y is the mean of y, or we call it y bar, okay? That's just a kind of a Greeky symbol for average of y. So I could take the average of all the known budgets I have from the agencies I collected and say, well, you're probably close to the average. So if I didn't know anything about you, the average would be the very best prediction of where your budget is. It would be better than just a wild guess, okay? So I know that your budget might be really high, it might be really low, but it's got to be somewhere near that average, okay? That's the very best we could do. In regression, we're trying to better that line, okay? We're trying to say, you know, there's got to be a better way than just the average to find out, you know, how this works. So when we actually graph a regression, we're taking a piece of information about you. Well, what if I knew how many employees they had? Maybe that could be more information that would give me a better prediction on how much their budget is. So not only do I know the average of Y, but I also know some other piece of information, how many employees you have. And so I can take that average of Y and I can take the other new information, the independent variable, how many employees do you have, and I can do some calculations to see how that piece of information deviates away from my average. So that's why we call it deviation, okay? And we can kind of account for how those little data points deviate away from the mean and how they deviate toward a hypothetical line that we think fits better. Okay, so that's what all these little calculations are on this slide. Is we have explained deviation, unexplained deviation, we square those, and it basically tries to kind of reiterate that over and over again until we get to a prediction that will work. Okay, and this is how those little calculations work. We're going to stop right here, and then I'll show you in the next video how this starts to go down in SPSS.